Hi there. We're continuing our work with particle motion here. Now, up until this point, many of my videos, we've been using our graphing calculator to help us out, but I want to spend some time on some examples that you need to be able to work without your calculator. Now, because these are with particle motion, I will encourage you to make sure you have seen my video on the 5 commandments of particle motion because I think that really do help you. I'll be sure to link it in the description below. If you haven't seen that video, it's one that you really want to go back and look at because it gives you kind of this foundation for your work with particle motion and how important particle motion is on the AP calculus exam, as it's usually one of the 6 free response questions. So, knowing all of that, let's go ahead and get started. For this one, we're being told that a particle moves along the x-axis for time t is greater than 0. And here is our position equation. Notice that position is measured in feet and t is measured in seconds. We're looking for the average velocity between 1 and 2 seconds. Now remember, average velocity, that's going to indicate we need to do the slope the algebra way. So we're doing part A here. We're going to do the average velocity is the position, the difference in the position over the difference in time. And remember, when I say slope algebra way, you really want to think of this as y2 minus y1 over x2 minus x1. Now the position at 2, so you've got 8 and then 16, so 8 minus 16. Let me make sure I'm writing this down. 8 minus 16, and then minus 6 plus 1. So that's going to be negative 8, negative 14, plus 1's a negative 13. And then we'll plug in 1. So I've got 1 minus 4 minus 3 plus 1, and that's going to give me negative 5. And then I've got 2 over 1, so we've got negative 8. Now I've got to use the correct units. So the positions were on top. That is in feet. And the time is on the bottom, and that is in seconds. And that's how we calculate the average velocity. We're doing it the slope algebra way. Now, on B, we're asked for when does the object move to the left? So we're going to need the velocity. I'll go ahead and take the derivative since velocity is the derivative of the position. And I'm going to set it equal to 0. Now, if you are remembering curve sketching, you're going, oh, we've done this. You're right. We have done this. Okay, it's the same technique, but we're applying it to particle motion. So I factored our velocity. I found that t will be negative 1/3 or t will be 3. Then I go to my number line. I'm not really concerned with the t being negative 1/3 because I was told the domain was t is greater than or equal to 0. But I need to test the velocity around t equals 3. So on the left, I'm going to test t equals 1. So I get 3 minus 8 is negative 5, minus 3 is still negative. And I'm going to test on the other side, I'll test t equals 4. That's 16, 48 minus 32, excuse me, 16 minus 3 gives me a positive number. So the particle moves to the left. On the interval from 0 to 3 because the velocity is negative there. Now notice I stopped it at 0 because of the domain. Okay, let's look at C. Using appropriate units, find the values of P prime of 3 and P double prime of 3. Okay, so P prime of 3 is equal to the velocity at 3, and we found the velocity at 3 was 0. And then we'll do P double prime. So we'll need to find the equation. That's going to be 6t minus 8. And if we find that at 3, we'll have 18 minus 8, which is 10. So this is the acceleration, which is feet per second squared. All right, now use these values to describe the motion, the particle's motion at t equals 3. So since the velocity is 0, but the acceleration is not, the object has stopped for a moment to change direction. And again, if that did not make sense to you, please watch my 5 Commandments of Particle Motions video, because that is one of the 5 commandments. The object is momentarily stopped and changing direction. And that is because V of 3 is 0 and A of 3 is not 0. If A of 3 had been 0, we would not be able to say this. All right, now D, what is the maximum volume on this interval? So this is talking about extreme value because you have an interval, okay? So on the interval from 1 to 3, we are going to test those endpoints, but I also need to know, does the object have a maximum or minimum velocity? We're looking for a maximum velocity. So I need the velocity's derivative, which is the acceleration, which is the second derivative of the position, which we found to be 6t minus 8. So if that is equal to 0, then I know that t will be 4/3. Now I need to know what happens at 4/3. So I need the velocity at 1, I need the velocity at 4/3, and I need the velocity at 3. I'm going to scoot this up so we have a little bit more room. Now remember, I'm plugging these in velocity. So here's my velocity equation. When t is 1, I get 3 minus 8, which is -5, minus 3, which is -8. At 4/3, it gets a little bit complicated, so I'll write this one down. 3 times 4/3 squared minus 8 times 4/3 minus 3. So that's 16 over 9 times 3 would give me 16/3 minus 32/3 minus 3. So that's going to give me, let's see, negative 16/3 minus 9/3. So I get negative 25/3, which by the way is -8 1/3. So I know that's not the absolute max because this one is actually higher. Now let's put in 3. So I get 3 squared, 9 times 3 is 27 minus 24, which is 3, 3 minus 3. So I get 0. So the maximum volume, I'm sorry, maximum velocity is 0 from t equals 1 to t equals 3 because it's the highest value on that interval. All right, finally, our last part of this question, total distance. All right, so I've got an interval from 1 to 5. Remember that the object changed directions at t equals 3. We learned that in part C. So when I do total distance, I've got to do the distance from the beginning to the turn. So I'm going to do the distance from the beginning, which is 1, to the turn. And then I'm going to do the distance from the turn to the end. And that's an absolute value sign there. All right. And these are position. Okay. Now, some of these you may have already found, like the position at 1 we found was -5. So I can still use that. Now we want the position at 3. I don't think I had the position at 3, so I've got to come back up here to my position equation. and plug in 3. That gives me 27. Do a little side calculation here. 27 minus 36 minus 9 plus 1. So that gives me negative 17. Now I'll use that on both of them, and then I need the position at 5. So the position at 5, let's see, I get 125 minus 100 minus 15 plus 1. So it's 25, 10, 11. So I can finish up here with my total distance. I've got 12 and I've got 28, which gives me a total distance of 40 feet for my total distance. But remember, total distance is about the distance from the start to the turn plus the distance from the turn to the end there. Friends, this is a really good non-calculator particle motion. Look at everything we were able to cover in that. It's going to be one you want to definitely keep handy with your notes. I do have one more for us, and this one is a calculator-driven question. So we feel free to use your graphing calculator on this one, and it comes from a table. Another approach we see with the particle motion. All right, so we've got a table, flies in a straight line. That's important. With a positive velocity, and you're given in miles per minute. And so the chart here gives you values for the velocity. So for part A, we're looking for the average acceleration. Remember, we just did this. Oops, and I wrote velocity. Average acceleration. And we're going to have to do that at the slope algebra way. So we're doing the velocity at 20 minus the velocity at 5 over 20 minus 5. Go to your chart to find these values. Velocity at 20 minus velocity at 5 over 15. So that gives me negative 4.7 over 15. And you can punch those into your calculator. I keep a nice little for function for these simple, just arithmetic type answers because I want to have them handy. And I'm definitely going to write this one in 3 decimal places. So it's negative 3.13, and that's in miles per minute squared because it's acceleration. All right, so look at B. B's asking you, where is the acceleration guaranteed to be equal to 0? Friends, this is asking you, where is the derivative of the velocity? Where's the derivative of the velocity guaranteed to be 0? This is Rolle's theorem. Rolle's theorem is asking us, or Rolle's theorem guarantees us that the derivative will equal 0 if function's continuous, the function's differentiable, and the y values are equal to each other. So where do you see the y values to be equal to each other? I see it here and here. I see it here and here. So I've got between 0 and 15, and I've got between 20 and 30. Okay, we've got to explain why. By Rolle's theorem, A of t will equal 0. A of t will equal 0 because velocity is differentiable, which also guarantees that it's continuous, and v of 15 equals v of 0, and v of 30 equals v of 20. Okay, go ahead and state Rolle's theorem. It'll be very important that you do that. All right, look at C. Does the data represent velocity values moving away from its port of origin or returning to its port of origin? So remember, the velocity we were told was positive. Remember, we highlighted that at the very beginning. With a positive velocity, you are moving away from the point of origin. So we'll say that since the velocity is positive, the plane is moving away from its point of origin. Okay, last one. Then D says, here's a function, and it's used to model the velocity in miles per minute. According to this model, what is the acceleration of the plane? What does this value indicate about the velocity at t equals 23? So this is asking you, what is the value of the acceleration? What is the value of the derivative here? So because we are using our graphing calculator, I'm going to switch our screen so we can see it. So you can see I've already taken a moment to put in this function, this velocity equation in my graphing calculator. If you need to pause the video so you can do that, please take a moment to do that so that we don't move on without you. But I definitely want to be aware of your time. So we are looking for the acceleration, which is the derivative of this function we were given. And we want the acceleration at 23. So we want the derivative of this graph at 23. Now, something to be mindful of when you graph this on your window, I'm going to start it at 0, but I've got to go all the way out to 23. So I'll put it to 25, let it graph, and then we'll ask it for the derivative here. We'll let the calculator do the heavy lifting with it. So let it graph, and then we'll second trace. We'll use that feature with the derivative. So second trace, option number 6. It doesn't really prompt you for anything, but this is where you're going to type in 23. And you can see the derivative value there is negative 0.408. Now I'm going to go ahead and put units of measure here. So this was in miles per minute squared because it's acceleration. So we've answered the what is the acceleration part, but it asks us what does this value indicate about the velocity? So remember, acceleration is the derivative of the velocity. If it's negative, the velocity is decreasing. At t equals 23, because a of 23 is negative. So I hope that helps you, gives you a non-calculator as well as a calculator example of free response questions. If you have comments or questions or something you'd like to see a video of that I haven't done yet, feel free to leave it in the comments below. Don't forget to like and share. That way you get a notification every time a new video is posted. Bye for now.